Section 9.4 is all about models for population growth. I have that our goals are to solve problems involving the law of natural growth and problems involving logistic growth. It should really just be solve problems involving logistic growth because natural growth is just so easy. There is one problem involving natural growth on your lab. So since there's not one in the textbook, there's not one in your WebAssign. So I took this example back from the first section where we were introing differential equations. It says that the population of field mice on a secluded island in the absence of predators, the population growth rate will be proportional to its size. That's natural growth, where the population is, the growth rate is proportional to its size. So it says, write this as an equation if the population size, P of t, and the constant of proportionality is 0.5. So this is example 2 from section 9.1, and we're kind of modifying it. So first let's just write this as a differential equation. dp dt is equal to your proportionality constant equals 0.5 times p. Now we know how to solve this thing. This is a separable differential equation, and we know how to solve those now. So we would have that dp over p is equal to 0.5 dt. I would plot integrals in front of those, and I would see that the natural log of p, it's a population, so I'm not even going to bother with an absolute value, is equal to 0.5 t plus a constant. So p is equal to e to the 0.5 t plus a constant, which is equal to some other constant, which is e to the c times e to the 0.5 t. If you're given initial condition, if the population at time 0 is equal to p sub 0, then p at time t is equal to p sub 0 times e to the 0.5 t. You did problems with exponential growth back in pre-calculus, most likely. We just called them PERT examples or NERT examples, where you did P e to the RT. So that's natural growth. We're going to concentrate on logistic growth. So here's the law of natural growth. If K is positive, it increases. If it's negative, it decreases. There's the pretty solution. If you have an initial value problem, then the number sitting next to e raised to the power is the coefficient. And let's see, another way of writing it is your net relative growth rate is equal to 1 over p times the derivative. If we could modify it by adding in something to account for harvesting or immigration or increasing for births, decreasing for the death rate, things like that. But we're going to move on to the logistic model because it comes up in so many application problems. At the very beginning, things look like natural growth, but then growth starts to slow down as it starts to reach what's called its carrying capacity. This applies to populations, it applies to the spread of new technology, it applies to the spread of information. The simplest expression for relative growth rate is that 1 over p dp dt, so 1 over the population function times the derivative, is equal to some proportionality constant times 1 minus p over the carrying capacity. That's what makes it slow down as it gets closer to the carrying capacity, which leads us to the logistic differential equation. The logistic differential equation. dp dt is equal to proportionality constant k times the population times 1 minus the population divided by the carrying capacity or the maximum population. So we're going to solve one of these step by step. Then we'll notice that the pattern will always be the same, so you can just memorize this pattern and use that to solve logistic problems. Write the logistic equation with k equals 0.5 and carrying capacity m. This one says to explore the direction field. So I'm not going to draw it, we're just going to present it and look at it. Example 1. So my k is 0.08. So dp dt is equal to 0.08 times p times 1 minus p over 1,000. So thinking way back to section 9.1, we talked about logistic models some. There was an equilibrium at its carrying capacity and an equilibrium at 0. So think about it. If the population is equal to 0, there's no incentive to grow. When it starts, your growth rate is proportional to your population, so it's stable there at 0. If your population is equal to your carrying capacity, then you would have 1,000 over 1,000 here. This would be 0, so your derivative would be 0 again. And there's the picture that illustrates that. If you have a population that's less than the carrying capacity, it wants to get there. If you somehow have a population that's bigger than the carrying capacity, it wants to decrease and get there. This is a stable equilibrium because it really wants to be there at 1,000. It depends only on P, not on T. So at each level of population, it has the same slope because it only matters what the population is, how fast it's growing. That makes sense according to our model. So there's all the pretty pictures. Now, the logistic model is a separable differential equation. I'm going to solve it for you so you never have to solve it again. You can just use the pattern that we create when we solve it. So let's look at this separable differential equation. dp dt is equal to some constant k, p, times 1 minus p over m. So we separate it. dp over p times 1 minus p over m is equal to k dt. We throw integrals on there. partial fraction decomposition. 1a over p. Now let's write it as 1 over p times 1 minus p over m is equal to a over p plus b over 1 minus p over m. So 1 is equal to a times 1 minus p over m plus b times p. Oh, you notice we're going to be plugging in those equilibriums. So if p is equal to 0, then 1 is equal to a times 1 minus p over m, which p over m would be 0, so a is equal to 1. If p is equal to, and let's say p is equal to m, then here I would have 1 minus m over m, so my a would disappear, so I would have 1 is equal to b times m. P is equal, yes, okay, making sure I'm right. So 1 over m is equal to my b. So let's look at the left-hand side. I have the integral of a over p, so 1 over p minus 1 over m over 1 minus p over m dp. And then we like the right-hand side. It's super easy. So this is the natural log. I'm not going to put absolute values because it's a population, it's positive, of p. This, let's do a little bit of u substituting. I'll do it over here. U is equal to 1 minus p over m, so du is equal to minus 1 over m dp. Well, I have 1 over m dp, so this is going to be, that was a plus because this was a plus, but now it's a minus. I knew what was coming. So it's going to be minus the natural log of 1 minus p over m is equal to kt plus c. Okay. Make sure I didn't mess anything up. So I found my u was equal to the denominator here. 1 over m was my b. I put it on top. Luckily, I had it there to be multiplied by the dp. I needed a minus sign, so I put a minus sign here. Now I'm going to use laws of logarithms to write this as the natural log of p over 1 minus p over m is equal to kt plus c. Well, you've done enough separable differential equations by now. You probably have a pretty good idea what's going to happen. I'm going to make each side the exponent of e. When I make this side the exponent of e, I end up with p over 1 minus p over m is equal to e to the kt plus c, which is equal to e to the kt times e to the c, which is just a constant, so I'm going to call it a, times e to the kt. I'm going to take a break and copy it onto another sheet of paper, and then we'll carry on. Okay, I went ahead and did some algebra here because there's a lot of algebra going on. So first thing I did is I just copied over this without the intermediary there. Then I multiplied this side by m over m. That way I ended up with pm over m minus, the m's canceled, so m minus p. Then I multiplied both sides by m minus p, but for some reason I put it over here and put the pm over there. Doesn't really matter. My goal was trying to isolate p because that is my goal, is to get a function for p. So then I left this term over here. I added p times a e to the kt to both sides. So I factored out the p. Then I divided both sides by the m a e to the kt. Now I'm going to divide numerator and denominator of this by a e to the kt. I want it to disappear up here. I want just that m left by itself up top. So that leaves me with the m up top. Here I have m over a. When I divide by e to the kt, I get e to the minus kt plus 1. But this is just a constant. So this is equal to carrying capacity over some number, and I'm going to name it A1 just so we don't get confused, e to the negative kt plus 1. So this is something that you're going to get every single time. If you start with the equation in this form, dp dt is equal to kp times 1 minus p over m. Then your k is going to be a negative k right here. Your carrying capacity is going to sit on top plus 1. Your population function will look something like that, and you just need to figure out what this constant is if you have an initial population. So if p at time 0 equals p sub 0, then you can determine what your a is, because then p sub 0 has to be equal to m over e to the 0, so a plus 1, which implies that p sub 0 times a plus 1 is equal to m. So a plus 1 is equal to m over p sub 0. So a is equal to m over your initial population minus 1. I don't memorize that. I usually just plug it in and figure it out. Here's the pretty answer. They did the math slightly differently on the PowerPoint. That's okay, because you're just going to memorize this anyway. So if we start with our logistic problem where we have dp dt is kp 1 minus p over m, we end up with population is carrying capacity, some constant e to the negative kt plus 1, and it has the 1 first here. I don't care. Either way works because you can add 1 first or last. And then your a is equal to m over p sub 0, initial population, minus 1. Now, if you look at this limit of this function, p sub t here, look at the limit as t approaches infinity of m over 1 plus a e to the minus kt. As t approaches infinity, this is approaching 0 because you have e raised to a negative power. So you have 1 over, or m over 1, which is just m, which means in the long run, eventually, the population approaches the carrying capacity. That's the horizontal asymptote of this model. So, write the solution of the initial value problem. Use it to find the population sizes P of 40, P of 80, and at what time does the population reach 900. So, I have dp dt, derivative of population with respect to time, is equal to 0.08 times p, 1 minus p over 1,000. So that's my m. This is my k. In order to be an initial value problem, remember it needs an initial condition, and my initial population is 100. So, population is equal to m living on top of 1 plus a e to the negative 0.08 t. So far, so good. Now I use my initial condition to figure out what a is. 100 is equal to 1,000 over 1 plus a. So, 100 times 1 plus a is equal to 1,000. 1 plus a is equal to 1,000 divided by 100. So a is equal to 9. Like I said, I don't memorize what it is. I just plug it in and solve it each time. P is equal to 1,000 over 1 plus 9e to the negative 0.08 t. We want to find the population sizes P of 40 and P of 80. Well, not sure why that's blurry. That's disturbing. Okay. And now my PowerPoint went a little crazy there for a minute. I'm going to pause. Plugging 40 and 80 in is really easy. Even though there's a typo there, this is really where I plugged 80 in. I'll fix that when I upload the actual PowerPoint for you. That should be P of 80. I really did plug in the right number there. More interesting is solving the equation determining when the population reaches 900. That's something you might not have done for a while. So I'll go over solving that equation. First thing I would do is multiply both sides by the 1 plus 9e to the negative 0.08t. Then I would divide both sides by 900. I would simplify that. 1,000 over 900 is 10 over 9. So 1 plus 9e to the negative 0.08t is equal to 10 over 9. But now I would subtract 1 from each side, which is 9 over 9. So I have 9e to the negative 0.08 t is equal to 10 over 9 minus 9 over 9, which is 1 over 9. Then I would divide both sides by 9. There's a lot of 9's going on. E to the negative 0.08 t is equal to 1 over 81. I would take the natural log of both sides. So natural log of e raised to something is just equal to the something. So t is equal to the natural log of 1 over 81 divided by negative 0.08, which is about, natural log is right here, 1 over 81. Close the parentheses and then divide by negative 0.08. And I get about 54.93. So let's see, this is in years, let's see. Doesn't tell us. It doesn't tell us what units. So 54.93 units of time. And we have a pretty picture, and it shows us where the function crosses the line, population equals 900. Okay, here's a practice problem. What is the carrying capacity? What is the derivative at when the population is equal to 0? And when will the population reach 50% of its carrying capacity? First thing you need to do is rewrite it in that format of the logistic differential equation so you know exactly what your K is. So give it a try, then we'll meet back and compare answers. How do we do? So first thing I had to do was rewrite it. So I factored out 0.4p, so I had a 1 there. I needed to figure out what I had to multiply by, so I would have 0.001 to factor out the 0.4. So I just did a little equation over here and realized it was 1 over 400. You can figure that out however you need to. Make yourself a little algebra equation, whatever you need to do. Here's the answer to part A. Your carrying capacity is 400. I got all excited and went ahead and wrote down the answer to the differential equation before I went back and answered A. But I put carrying capacity, 1 plus A, E, and since I had it in the format of the logistic differential equation, my K was 0.4, so minus 0.4t. I computed my A by looking at the initial value, the initial population of 50, and I went ahead and solved. Then I answered, what is the population at time 0? At time 0, population is 50, and when the population is 50, the derivative, I just plugged 50 into my function for the derivative. Easy enough. And then part C was kind of like the last problem part of the previous example. I had to set half of the carrying capacity, 200, equal to the population function and solve using logarithms. Easy enough. One more practice. And this one's an application problem. I'll take a break and let it clear up. So biologists stocked a lake with 400 fish and estimated the carrying capacity, the maximal population of fish for that species in the lake, to be 1,000. The number of fish tripled in the first year. Assuming the size of the fish population satisfies the logistic equation, find an expression for the size of the population after T years. A little bit different. We're not given that proportionality constant. We're going to have to figure it out from the fact that the number of fish tripled during the first year. So let's write down what we know. We know the initial population. P at times 0 is 400. I know the carrying capacity, 10,000. I know that the derivative of population with respect to time is equal to some k times p 1 minus p over 10,000. So there's my logistic differential equation. So P is equal to 10,000 over 1 plus A e to the negative kt power. I need K and I need A. Well, I don't need K to figure out what A is, because A is the value of the population when T is equal to 0. And when T is equal to 0, then e to the 0 is just 1. So 400 is equal to 10,000 over 1 plus A. So 400 times 1 plus A is 10,000. So 1 plus A is 10,000 divided by 400. Times divided by 25. So A is 24. In real life, the A's don't always come out to be nice, friendly whole numbers. So P is equal to 10,000 over 1 plus 24 e to the negative k t. Now I use the fact that the population tripled in the first year to figure out what my k is. So in the first year, I went from 400 to 3 times 400. 1,200 is equal to 10,000 over 1 plus 24 e negative k times 1 is just negative k. So now it's exactly like the problems we've been working, where we had to figure out how long it took to reach a certain population. So 1,200 times this denominator equals 10,000, so 1 plus 24 e to the minus k is equal to 10,000 over 1,200. So 24 e to the negative k is equal to, I'm just going to write it as 100 over 12. I just got rid of those last 2 zeros there. And there's still a 1 there, so I will subtract 1. I'm going to do the arithmetic and figure out my k, and I'll meet you back. Now, I'm going to take advantage of some laws of logarithms to write this without a whole bunch of decimal points. because I took e to the negative k was equal to 22 over 3. I simplified that 100 over 12 minus 1. And then I divided both sides by 24, and I ended up with 11 over 36. So I knew that k was equal to the natural log of 11 over 36. Actually, negative k was equal to the natural log of 11 over 36. So this is equal to 24 e raised to the natural log of 11 over 36 times t. But remember, e raised to the natural log of something, they undo one another. So this is really 10,000 over 1 plus 24 times 11 over 36 to the t power, which is a little friendlier than having that decimal, and it's a lot more exact. So when you figure out how long it will take the population to increase to 5,000, it will be a more precise answer. So do that now. So did you remember how to solve those equations? I just set it equal to 5,000. I ended up with 1 plus 24, 11 over 36 to the t is equal to 2. I subtracted 1 from each side, divided by 24. Then I had my exponent was my variable, so I threw logs at both sides. The exponent fell down, and I ended up with about 2.68 years. Now, there are other models for population growth that take into account other things, like harvesting. We talked about that earlier. For some species, there's also a minimum population level in addition to the maximum. We're not going to solve any of those types of problems. Concentrate on those logistic problems. You got this.